Okay, well, welcome to the first review session for Engineering 210 circuits. Uh, in these review sessions, I will be going over just a couple. I'll start by going over some of the concepts you learned in a given week, and then go through some example problems, and I can stop along the way to answer any questions you guys might have as I'm doing this. Feel free to leave comments in the chat or speak up for those of you that are here in person or actually in the Zoom call, you know. Um, and then afterwards yeah. Um, please make sure you are muted if you are not speaking. Okay. So, let's get started. Hopefully you can all hear me and I'll see the screen. So to start, most important thing that you've learned so far is V equals IR. That's like kind of the foundational thing of circuits. This is Ohm's law. Before we can talk about that, though, we have to talk about the stuff you've learned in terms of what a circuit includes. So we have voltage sources, we have current sources, we have resistors, and we have our dependent sources. And that's pretty much everything I believe you've been working with so far. So I will briefly talk about what each of these means. So V equals IR for this portion of the class primarily refers to resistors, right? If we have a voltage source and it is connected to a resistor, V equals IR tells us, in a way, it's much more straightforward if you think of it as I equals V over R in this case, that if I have, say, 10 volts here and I have a 4 ohm resistor here, ohms is just the unit for yeah, I'll go over the units, right? We have 10 volts, 4 ohms. From physics, that's kind of what that's talking about. Doesn't really matter for the purposes of this class, just know that those are the units. If we want to know, okay, what is the current flowing through this resistor, we say, okay, V equals IR. We can fill in V, and we can fill in R, right? And then we solve for I, and you would get 10 fourths, or what's that, 2.5. And the unit for that is amps. Amps is current. Yeah. So that's Ohm's law. Hopefully you are all clear on that. Next up, uh, oh, I'll also go over Ohm's law in terms of a current source. So if we had the same thing, right? And let's say this is providing 2 amps and this was 3 ohms, then okay, we already know the current here, right? The current here is 2 amps. Since we only have one loop, the current is the same everywhere in a loop. So everywhere here we have 2 amps. And then we want to say, okay, what would the voltage be on this resistor? Then we would use V equals IR just in its normal form, right? And we'd get V equals 2 times 3 equals 6 volts. Very cool. The deal with the dependent sources is that they don't have a set number. They have something like, instead of a number, you'd put in an expression like, I don't know, three. I'll have better examples later, but it's the same thing. It's just some expression. Um, I'm gonna kind of try to go through the theory bit fast because hopefully you've learned that in class, and I'll spend most of the time here just talking about practice problems. So the other important things are KCL and KVL, Kirchhoff's current law and Kirchhoff's voltage law. So the current law is saying that if you have some circuit, then, so this is current law. What it's saying is that at every node, we can say that the sum of all of the currents is equal to 0. What that's saying is if we say define positive current as going out, which you do for this class, then I1 here, I2 here, I3 here equals 0. The other way to look at this is you say, okay, if I kind of looking at this, maybe you don't get it quite yet, but in a couple weeks, you'll probably understand the current's probably going to be flowing something like that, right? So what Kirchhoff's current law is really saying is that the current going in is equal to the current going out. So if we were so yeah, basically you'd say this as I1 equals I2 plus I3, where I1 in this case would be thought of as negative because it's going into the node. Kirchhoff's voltage law, I'll write this over to the side. Into node is negative, out of node is positive. So for KVL, on the other hand, it's saying that the sum of the voltages in a circuit is zero. That's the math. What it actually means is if we have some circuit and we have some voltage source and then three resistors or some other components, what it's saying is the voltage rise given by this voltage source is going to be equal. So we can think of this, it has a plus and a minus there. It's going to be equal to the voltage drops across these three resistors in total. So that's saying like if we say that this is 0 volts, then it's going to go up by some amount here, and then it'll go down here, it'll go down here, and it'll go down here again, and we'll end up back at 0 volts. So in this case, let's say this was 10 volts, this was 3 ohms, this was 4 ohms, and this was also 3 ohms or something. Then I will spare the math, but with some tricks you'll probably learn quite soon in the class, this would have a drop of 3 volts, this would have a drop of 4 volts, and this would also have a drop of 3 volts. And as you can see, here it goes up by 10 volts, and then it would go down 3 volts, down 4 volts, down 3 volts again. This sums to 10, and we'd end up back at 0 volts here. That's what Kirchhoff's voltage law is saying. And the neat thing is that you can say this for any loop. So it's the same as if we were to go around here. If we started here and went to here, we'd end up with the same back at 0 volts. Same thing if we go around this loop, we'd end up at 0 volts. And even it's the same thing if we went around this loop. So that's kind of counterintuitive. But if you look at it from the perspective of this arrow, right? Here, from this point to this point, we're going up a voltage, and then from this point to this point, we'd be going down. Okay, then last thing I will talk about, which is relevant to this, what we define as positive and negative voltage. So when we are kind of going around a loop, or if we're thinking about current and voltage, this is also relevant in power, which hopefully you've learned about because you've all done the homework. Power is current times voltage. And for this, the sign of power is very much dependent basically on the sign of the voltage. The sign of the voltage depends on what direction so if we have some kind of like box and it has a current flowing through it, yeah, I'll say down. This is the current, and it has some voltage. If the voltage, I will write this in words because people get confused about this for a while because it's kind of counterintuitive. If the voltage drop is in the same direction as current flow, so I'll underline drop, the voltage is positive. So this sounds weird because like if it's dropping, it's negative, but for the sake of making your math easier, this is the case. So that would mean that this would be a positive 3 volts, this would be a positive 4 volts, and this would be a positive 3 volts here. Because if we're looking at the current like kind of going like that, then this drop here, plus minus, is in the same direction as that current flow. Same thing here and same thing here. However, for the voltage source, the current flow is not in the direction of the drop. The current flow is in the direction of the voltage rise. So here, this would actually be a negative 10 volts in terms of like a KVL equation. So, and vice versa. I'll just say that. Oh, oopsie, sorry. Okay. And vice versa. I could definitely go into more detail on this, but hopefully you all know these basics by now. So I will get into practice problems. Of course, if you have any questions as I'm going and you want more explanation, I'll try to like talk through as plainly as I can what I'm doing as I go. But yeah, if you want any more explanation, feel free to ask in the chat. I'm going to start by kind of showing an example of this from your homework. So I'll do two of the homework questions. Hopefully you guys already got these, but real quick, I will go over them. So this was question 3 on your homework. Uh, Give me a sec to write all this out. And then it was, oh, and then it also gives you that there is 3 amps here. Yeah. And then it's asking you to find this current, and this current, where this is I1, I2, and I3. So since we're dealing with currents, we probably want to think about KCL, Kirchhoff's current law. And what that's saying again is that the current going into the node equals the current going out of the node. So basically, we want to write a bunch of equations at each of the relevant nodes where it'll talk about relating these currents to each other. One thing I will say is that probably like 75% of this class is using the things you've learned to write a system of equations and then solving the system of equations. So that is exactly what we're going to do here. So if there's 3 unknowns we have, and if we can get 3 equations and we have 3 unknowns, then you can solve for this. So I'll start by doing a KCL equation. Um, I'll start here, right? So what would this be? Remember, it's saying that the sum of the currents at a node is equal to 0. So if we start, we can see, okay, coming in from the left here, we have 3 amps going in. So that would be negative 3 amps, as we defined earlier. And then going out, we have I1, we have I2, and we have that 1 amp current source at the top. Again, current sources, it's kind of defining, okay, regardless of whatever else is going on in the circuit, we have one current, we have 1 amp flowing along this path. So that would be, if there's 1 amp flowing here, that means through this whole line, since there's no branches, there is 1 amp flowing.
I have a question. If
Mhm.
someone define, for example, if I define the current going in to be positive and the current going out to be negative, there is nothing wrong with that as long as I'm consistent, right?
Um, yeah, you'll get the same answers. However, I would say just kind of for the sake of your graders on quizzes and stuff, it's a lot easier for us if you get your head around it with current going out being positive and current in being negative, just because that's how it's going to be handled for the rest of the class. That's how they're going to teach it. Uh, if you really want to, like you can keep doing it the other way. The math will be exactly the same. It's like if you added a negative sign to both sides. But
Mm,
yeah, your intuition is right. I would just highly recommend trying to think about it without being positive and being negative.
okay, thank you.
No problem. Okay, so yep, we have 1, 2, 3, 4 ways out of this node. We have 1, 2, 3, 4 things here, and we say it equals 0. And if you want to simplify this equation, move your constants to one side, move your not constants to the other side. We get like I1 plus I2 equals 2. And that would be your first equation. We have one equation, 3 unknowns. We still have a bit to go. Next, I'll do this point. So here, at this point, we would have 1 path, 2 path, 3 path. Or 1 path, it would be more like 1, 2, 3, based on the arrows we've defined here, right? So if we look at that top one first, okay, we have 1 amp going in, so we have minus 1 amps. And then we also have minus I2. And then finally, we have positive I3. If you want to rearrange that, don't really need to, but just keeping it all consistent. And then last but not least, we can look at this point. Here, we'll have I1 going in, I3 going in, and then this third branch. However, we know what the value of this third branch is. Since the question gave us that there's 3 amps right here, and this is all one path, That means if there's 3 amps here, there's 3 amps here, there's 3 amps here, there's 3 amps here, and there's 3 amps coming out of that node, right? So we can write this as negative I1 minus I3 plus 3 amps, because the 3 amps is going out equals 0. And then, for those of you who've like taken linear algebra or anything, we have three linearly independent equations, basically just meaning we have three equations where they are actually different equations. So this one has I1 and I2, this is I2 and I3, and this one has I1 and I3. None of those are the same equation. They all have different variables. That means you can solve them as a system of equations and get your final answer. Um, and that just kind of comes down to algebra, which is something that is hopefully assumed as a prereq to this course. So you'll get a lot of practice with your algebra on the quizzes in this class. Um, Real quick, I could try to do some of this quick. If you combine these two equations, just kind of add them together, you'd get, actually that does not help, does it? I1. For the sake of the homework, often you can like put stuff in a solver, but it's good to practice this as well. I'll actually just do this. So here if we say I3 equals 1 plus I2, then we have a value for I3. Plug that in over here. I1 plus 1 plus I2 equals 3. And then we can define, this is like probably not the best way to do this. I'm just doing this very haphazardly. I1 equals 2 minus I2 if we move everything over to the other side. And then we can take that over here where we have I1. Oh wait, no, I1 is oh, I'm doing this badly. Sorry about that. Give me a sec. Pause for a moment. Um, oh, yeah, yeah, yeah. Fault. So you can solve it that way. However, a kind of a more straightforward way of doing it is you know that what is it? Yeah. Okay. You all did this on the homework, so I hope I don't have to go over it. But there's like I don't know how in depth I want to go. But if we have 18 volts here, then it goes down by 2 times 3 equals 6 volts here. This is actually this is what you use KVL for. Sorry, I'm rambling a bit. It's been a minute. Um, so I'll actually go over this. So if you have a KVL loop here, right? That's saying that the sum of all voltages equals 0. So if we define our loop going that way, we would have negative 18 volts plus 2 ohms times 3 amps plus 8 ohms times I1 equals 0, right? These are both V equals IR here to get voltages, where, we have our current and our resistance, our current and our resistance. And so that would be for this resistor and this resistor. And then if you solve this, right, you'd get 18 or negative 18 plus 6 plus 8I1 equals 0. Move everything over. 8I1 equals negative, or 8I1 equals 12. And then I1 would equal 1.5 amps. And then this you would plug into your other equations and you can solve for the other ones. And you end up getting I2 equals 0.5 amps and I3 equals 1.5 amps. Yeah. But the important part I wanted to show for this is really writing these equations out, and then you can use those to solve for your actual stuff. Once you get the equations, it's a matter of algebra. The equations are really the important part in terms of like understanding the content in this class. Okay. Moving on, I'll go over problem 4 on the homework, which is the one I saw most people have some issues with. We had two resistors, and over here we had a dependent current source. And this was asking for what is the power associated with the dependent or with the independent source. So it's asking what is the power of this? If we remember, power equals current times voltage. So that means we are looking for the current and the voltage associated with this current source. We already have the current, it's just zero point 0.2 amps. So we need to find this voltage. The nice thing about voltage is that if things are connected by a wire, then it's the same everywhere along the wire. So the voltage here and here is the same as the voltage so the voltage difference between these 2 points is the same as the voltage difference between these 2 points, and it's also the same as the voltage difference between these 2 points, because these are all connected by wires. So basically, what this is saying is, okay, if we can find the voltage here, which we could find by finding the current through here, since there's resistors, then we can find the voltage difference on that power source, or on that current source. So for this, again, you kind of just have to figure out how to write your equations to properly model the situation, and then you solve it. So for this, since we have two current sources, my mind goes to, okay, let's deal with Kirchhoff's current law. We have a current here, a current here, and a current here, right? We have 2.2 amps here. We have whatever V1 over 4 happens to be. And then we have this, which we can call, you can kind of just make up variable names when you want to. So let's say we call this IX or something. So let's say this is IX. So we can say that if we're thinking about this node, since this is going in and this is going in, we would have minus 0.2 minus V1 over 4 plus IX equals 0. So that's one equation. And then we need two equations to actually solve this. And what we can do is we can just define V1. So V1 is very simply going to be V equals IR, right? So it's going to be IX times 2 ohms. Then we can, plug that in. Minus 0.2 minus IX times 2 over 4 plus IX equals 0. This will become, if we move over the point 2 equals 1 half IX plus IX. Or, oh, this is a minus. So then we'll get, I think I'm missing a minus sign somewhere. Am I? Oh, no, no, we're good. Yeah. So 1 half IX equals 0.2, IX equals 0.4, right? So that's saying we have 0.4 amps going down through this middle section. So then if we want to find the voltage across this whole thing, right?
Hey guys.
Hello. Okay, thank you. If we want to find the voltage across this whole thing, right? So remember, we're trying to find the voltage difference between these 2 points. Then we want to find the voltage difference across these resistors. And for that, you can just use Ohm's law. If we have two 2 ohm resistors in series, together they will have 4 ohms of resistance. So that voltage will simply be Ix times 4, which is 0.4 times 4, which is 1.6 volts, right? Then finally, if we want to find that power is current times voltage, it'll be 0.2 amps times 1.6 volts, and that would get us 0.32 watts. And that would be the final answer. Or this end, you'd have to think about, okay, is this supplying or consuming current? If we look at the current source, it is defining the current as going that way. And here, the current is in the opposite direction as the voltage drop, so this would get a negative sign. And yeah, that's how you do that question. Moving on, I will do some different questions. Some of these are kind of similar, but there's not really too much to be quizzed on so far. So yeah, let me pick one real quick. Um, It's like kind of interesting. Um, okay, I'll go over this question as well. This has stuff to do with, I assume, actually, have you guys learned like combining resistors in series and parallel? I assume you have, but I saw it wasn't explicitly on the homework, so you might not have. If anyone wants to say in chat or just speak up real quick.
We did, but it's not gonna be in the quiz, I guess, because we did that this week.
Okay, you did that this week? Okay, then I will leave this for later. Yeah. Um, yeah, I'll do this. So give me a second to draw out the circuit. So actually, I'll leave these off for now. Okay. And then this was 3 ohms. This is okay. So this question, you want to find Vx and power of the 10 amp source. So how do we do that? Basically, same thing as every other question. You want to write equations that describe the circuit and then use those to solve for relevant values. And at the point you are in the course right now, that's pretty much just going to come down to using KVL and KCL equations. So we'll start with this pretty much in the same way as we did before. Um, I'll start by, hmm, I'll start with a KCL equation up here. And for that, I will define this current as a, let's say I1, and this one as I2, because both of those are still unknown. So I'll like label this as green or at node 1 or whatever you want to call it. We would have, and for these arrow directions, you can kind of guess whatever you want. Uh, if you end up guessing wrong, you'll just get a negative number, and that tells you the arrow or the current's actually going in the other way. But for this, the voltage source is pointing up, so it's probably kind of going like that, and this one's probably kind of going like that. So you can guess, and you'll usually get it right. But yeah, so here we know we have 10 amps going in, so we have negative 10, and then minus I1 plus I2 based on those signs equals 0. So that can be our first equation. Then our second equation, we can look at a loop around this way to do a KVL. So this is KVL, and that'll have, okay, what sign does this voltage source get? The current's going up, and there's a voltage rise, so that means it's a negative 10. And then for resistors, it's just always going to be positive, basically. So 10 plus 3 times, and then the current here is that I1 we defined earlier. And remember that I1 will go all the way around this way. So that's I1, that's I1, that's I1. So 3 times I1. This resistor here will have I2. And then finally, this resistor here, as I just said, will have 4I1. And then that will all equal 0. And if we solve these equations, let's see, we have 10 plus, this is 7I1 plus 3I2. And then here we have negative I1 plus I2. Okay. So these equations should work out, I think. Yeah, you just have to combine them a bit. Yeah. So, all right, I'll rewrite this in a slightly nicer way. And this one as, and then if we subtract one of the equations from the other, so if we subtract this one from the first one, we'll end up with 8, or no, that's not how you want to do this because you want to cancel the variables. Um, let's just say I2 equals I1 plus 10. And then we can say 7I1 plus 3 times I1 plus 10 equals 10. And then we have 7 plus 3, so 7I1 plus 3I1 plus 30 equals 10. And then you subtract it over, negative 20. Is that? No, I'm doing something wrong here, I think. Maybe. Wait. So I shouldn't be getting a negative there. I don't think. Um, Pause for a moment. 7 plus 3, yeah. 7, 2. Hmm, hmm. Let me see what happens here. So 10. Oh, okay, wait. Oh, actually, yeah, I think this is right. Yeah, okay, it's just kind of odd. Here, we will end up with a situation that I talked about earlier where you guessed wrong. Yeah, so then here we'll end up with I1 equals negative 2 amps. I don't think I did the math wrong. I think that's just how it turns out. Yeah. Yeah. And then if we take this and plug that back into our original equation, or one of just either of the two original equations, we'll end up with I2 equals negative 2 plus 10. I2 equals 8 amps. Yeah, okay. I second guessed myself, but no, that's fine. So what that's saying is that while I guessed that I1 was going in this direction, the negative sign on this 2 amps is actually telling me, okay, actually we have 2 amps going this way. That can happen even though the voltage source is facing that way. It's just it just can happen like that. How do we know that the current across the 4 ohm resistor is I1? So when we defined I1 for this first equation, we kind of just said, okay, there's 3 ways that this node is connected. It has 3 connections. We're going to call this one I1 because we don't know it. We're going to call this one I2 because we don't know it. And then this one we know is 10 amps. However, since we defined I1 here, remember the current along a branch is the same everywhere. So if it's I1 here, it's I1 here, it's I1 here, it's I1 here, it's I1 here. And so that I1 goes through the 4 ohms as well. And that's how we get that for this equation. Okay, so we're getting somewhere. However, we still need to answer the original question. We need to find Vx. So now that we have I2, we can find Vx pretty clearly, right? Vx, remember V equals IR. Vx is going to be I2 times 3. We have I2 now, so it's 8 times 3, and that gets us 24 watts. Cool. And then last but not least, find the power of the 10 amp source. So for power, now that we have Vx, we know that there are, I also completely used the wrong unit there. Sorry, got ahead of myself. 24 volts. Double check your units. It will be counted on the quiz. So this is our first answer here. I was thinking about power because that's the next section. But for this, for the power, now that we found this voltage of 24 volts, remember for power, we need the voltage here and the current here. Luckily, since we know the voltage here, this is connected by a wire. We also know the voltage here. It is also 24 volts. So to find the power of this current source, very simply, we can say P equals IV. The current is given, it is a current source, and then times 24. And then we want to look at the sign of that to figure out if this is a positive or negative power, if it's supplied or consumed. Remember what I said on that previous page. If the voltage drop is in the same direction as a current flow, the voltage is positive and vice versa. Here, however, the voltage rise is in the direction of current flow, so this will be a negative 240 watts. You can either like do that on the voltage, or I usually just ignore the sign until we get to that end and then fill it in here. And that would be your answer for that. So again, the process, as always, is use your KVL, use your KCL, get like some number of equations that matches your number of unknowns, and then solve. I have time for a couple more questions, so I will do some more. Um, let's see. I'll do this one short. Okay. Well, this one's kind of interesting.
Can you please tell again why the power was negative in the other question?
Um, can I go over again why the power was negative? Sorry, you're my.
Yes.
Okay.
Yeah.
So let me erase some of these lines. It's a bit busy here. So you understand that we found the voltage across this resistor to be 24 volts, right? And what that is saying is that in the direction of current flow, I2, there is a voltage drop of 24 volts between this point and this point, right? Since this point is connected by a wire to the same point here, right? You can see that. So if we have a 24-volt drop between here and here, then we also have a 24-volt drop like on our current source. Then, and it has the same sign here, so we have plus minus 24 volts. Our sign convention for power is that if we have a voltage drop in the direction of current, this will be positive. And if we have a voltage rise in the direction of current, then this will be negative. Let me flip these over. That's more applicable to the situation we're in. So this is how we define our currents, or our positive and negative for any component. So here, the current source, you can either think of I personally think of a current source as it just tells you what direction the current is going. So here we have a current source pointing up with 10 amps. So that means the current is going that way. And then if we look at the polarity of this voltage, the voltage is rising with the direction of current, right? So here, when the voltage is rising with the direction of current, then we call that negative. And that's when it is supplying power. Hopefully that helps. That's kind of I can go like more.
Yeah.
Okay, yeah.
No, thank you.
Yeah. So really just drill, this into your head. Say this to yourself a couple times. If the voltage drop is in the same direction as current, then it's positive. So it's like kind of, if it's backwards, it's positive. So That's why it can be a bit confusing, but you'll get the hang of it. Mhm. So next up, doing this question. This question's kind of tricky. I don't know if you'd get something like this on a quiz. There's a new teacher teaching this class, and I don't know what she's going to do. I will find out with the rest of you. But these are some questions from previous years, but everything is out the window now. So this is saying find the power of that Vx voltage source. And I don't, which information do they give you exactly? This. Oh, okay. So this question is kind of interesting. They give you that you have 15 volts here, and oh, this is Ix. So they give you that you have 15 volts across the resistor, but they don't actually tell you the voltage of this source. So we kind of have to work backwards to find out what the power of it is, because we both have to figure out, okay, what was its voltage and what's the current flowing through it. Okay, so to start with this, let's find out, okay, what information do we know? We know, okay, wait, I'll talk a bit more about how I think about this problem going in. So we want to find the power of that voltage source, which means we both need to find its voltage and its current. So for that, we need to find the voltage here and here, and we need to find this current, or we need to find this current, which is the same as Ix, because it's, connected. So all that, basically we just need to figure out what's going on in the circuit. Same thing as most of the rest of the stuff I've been talking about. Write your equations, figure out what you can do, and then use the values you figure out to figure out everything you need. So here, the only thing we really have going for us at the beginning is for this resistor, we know its resistance and we know its voltage. V equals IR, we know it's 15 volts equals some current times 5. This gets us that there are 3 amps going through here. So that's nice. This is 3 amps. That means here we also have 3 amps. Wow, so cool. Then if we look at this node, let's say we wanted to write an equation for it. And the reason we might want to do this is because you can see here we have something with Ix and here we have something with Ix. So if you were to, write an equation, you can solve it in just one equation. So here, if we look at this, coming in from the left, we have negative Ix. Coming in from the bottom, we have negative 0.5 Ix. And then out to the right, we have that 3 amps we just figured out. That's going to equal 0. And then if we solve for Ix here, we have 3 equals 1.5 Ix. So then that would leave Ix being 2 amps. Hopefully that's clear. I moved these two to the other side. Just algebra stuff. So now that we have Ix, we can figure out the rest of it. So now if we want to figure out the voltage, so okay, wait, so we've checked off this, right? We know the current is Ix. If we want to find the voltage, now we can look at KVL, Kirchhoff's voltage law. Remember that's saying that, if we look at a whole loop, whether it be this loop or this loop or this loop, then the voltage rise is going to equal to, so like here we know we have a negative positive because it's a voltage source. It's defined as this direction. The rise of the voltage here is equal to the voltage drop from here to here plus the voltage drop from here to here. So if we say, okay, we're going to do a KVL around this whole outer loop, then we can say, okay, negative Vx, remember, because the voltage is rising in the direction that we're kind of defining for this loop, and then plus 10 times Ix, I'll just write it as Ix for now, I'll fill it in a sec, plus we keep going around the loop here. So we've done this, the next thing we run into is here. And while you could write this as 5 times 3 amps, we already just know that it's 15 volts, right? Because that was given at the beginning of the question. And then there's nothing else on this bottom section, so it's just that equals 0. Luckily, we've already found that Ix, so plus 10 times 2 plus 15 equals 0. And then if we solve all this, we will get that Vx equals 35 volts. Now we have our voltage, we have our current. We can say that the power of that Vx is going to be IV, which is going to be 2 times 35, and that will give us 70 watts. And now we have to think about, okay, what is the sign? Same as before. Okay, we know that the current is 2 amps going that way, and we know that we have 35 volts that way. We see that the direction of the current is opposing the voltage drop, so then we have a negative power. And that would be how you do that. So again, same thing as before. Use the information you know, figure out some numbers, and then you want to use your KVL, your KCL, your KVL to solve for what you don't know. Get some practice, you'll get the hang of it. Yeah.
I have a question.
Mhm.
Why did you decide to use the outer loop instead of like the left-sided loop?
So the reason I did that is because we don't really, well, I guess you can. There's not really any difference. That's a good point. So since you know that there's 15 volts here, you also know that there's, same reason as before, you know that there's 15 volts here. So it's practically identical. The only difference is, like, in my mind, when I'm looking at this, like, thinking about the voltage of a current source is kind of like, it's harder to wrap your head around. Whereas for this, like, even if we didn't know that it was 15 volts here, but we knew it was 3 amps and 5 ohms, then you could figure that out again. So there's really no reason to do either. Yeah, once you have a voltage, then since these two things are in parallel, just like this whole section, it has 15 volts across it. So if effectively doing a loop here is the same as doing a loop here. Yeah,
All right, thank you.
no problem. Will this be posted on Canvas? Yes, this will be posted on Canvas. I will upload it to YouTube and then post the link. Cool. Okay, I have time for one more problem, I think. Can you always pick any loop? Yes, you can always pick any loop, but not every loop will always be useful. Yeah. The reason you can pick any loop is because, like, if you'll get to this in like a week or two, but generally when you're solving circuits, you pick a point to define as 0 volts. Usually you'll pick like right below the voltage source or something like that. And basically that's saying, okay, if I have 0 volts here or here or here, if I were to go around the circuit and then come back to the same point, then if I go up 10 volts, down 10 volts, I should, or like up 10 volts, then here down some number of volts, down some number of volts, I should end back up at 0 volts at this point. Otherwise, it just doesn't really make sense, right? And that's why you can pick any loop, because whether I'm going, okay, I start at 0 volts here, I go up 35 volts, I go down 30 volts, and then over here I go down another 15 volts, I'll end back at 0 volts right here. It's going to be the same thing if I go this way. And like, let's say there was another section of the circuit over here where it like had a resistor there and a resistor there, it should still be the same thing ending up back at 0 volts. Otherwise, like, you drew the circuit wrong or something very weird happened. But yeah, you can always pick any loop. Mhm. Yeah. Um, let's find one more problem to do. Um, that's like the exact same as your one more problem. I'm not doing that. Um, I assume you guys haven't learned. Have you learned source trans? I should really look at the class notes. Um, have you guys learned like source transformations at all? Does she post the notes? Is a better question. No, that's the wrong thing. Where is it? Sorry, give me a sec. Oh yeah, okay, wait. Files. Yeah, sorry. Zorman was teaching this course for like 5 years. So now that he's dean and moved on, I have to recalibrate to a new teacher. And by 5 years, Zorman taught this course for like 20 years. I think he taught it before most of us were alive. So he was very locked in. Um, but Dunning is doing it her own way, and I need to learn what order she is teaching stuff in. So, and she did not post her lecture notes, so I cannot learn what you guys have learned. Oh wait, maybe she did. I don't know. I'll just pick another question. I'll stop thinking about it so much. Um, uh, okay, this is like really similar to your homework question, like very, very similar to your homework question, but I'll do it anyway. I'll change the numbers around. Let's say this is 0.4 amps. Oh, sorry. This is 4 ohms. This is 2 ohms. Mhm. This is V1 over 5. And let's say we wanted to find the power of this current source. So hopefully you all kind of know how to do this. This is going to be basically the exact same process as for that homework question, just with different numbers. So again, we'll want to start. Oh, and this is V1. We'll want to start by doing a KCL here. So let's call this I1. So we can say, okay, we have 0.4 there. You have V1 over 5 here. So that's going to be negative 0.4 minus V1 over 5 plus I1 equals 0. And then that V1 is going to be equal to I1 times 4. If we do our math here, 0.4 minus I1 times 4 over 5 plus I1 equals 0. Then we'll have minus 0.4 minus, this will be 0.8 I1 plus I1 equals 0. And then this will get us minus 0.8 I1 plus I1, that would be 0.2 I1 equals 0.4. Then I1 would be equal to, multiply each side by 5, 2 amps. Then from that, we can find V1. So then V1 would be equal to 2 times 4, which would be equal to 8 volts. So then if we want to find this current, it would be 8 over 5. So here, this is going to be 8 over 5, which is 1.6 amps. So that's half of power, right? Because we have IV. So we found the I. And then for the V, the same thing as before. We want to find this whole thing. So 4 ohms in series with 2 ohms would be 6 ohms. So the voltage of that dependent source, sometimes they draw the symbol here to simplify that. It's the same as the voltage here, same as voltage here. So it would be IR, which is going to be I1 times 6, which is 2 times 6, which is 12 volts. So then finally, last but not least, our power would be I times V, which is 8 times 12, which would get us, I know my times tables, 96 watts. And then again, same thing as before. The current's going that way. The voltage is this way. So therefore, it's going to be a negative power, supplying power. Okay. Yeah, I think that's kind of it. There's not really any more topics to go over, I believe. Correct me if I'm wrong. I'll give you guys like 20 seconds to say something in the chat if there's anything else you want me to go over. Otherwise, I have 5 minutes left, so I'll end it here.
I've got a quick question about the power.
Mhm.
Where did you get the 8 from for the current?
Um, here, so we found I1, and then if we have I1 here, remember V1 is this, so it's the voltage of this resistor. So we plug this in here, and we got 8 volts. And then the current was defined as V1 over 5 for this dependent source, so it's 8 over 5. But the eight is from I1 here, which we found to be 2 amps. So we have 2 amps flowing in this branch, and then this is a 4 ohm resistor. So 4 ohms times 2 amps gets us 8 volts. Is that clear?
So then why did we multiply 8 volts by 12 volts to get 96 watts?
Um, Good point. I just did that wrong. Thank you for calling me out on that. Yeah, you're very right. This should be 12 times 1.6. I just did that wrong. It should be, yeah, 1.6 amps times 12 volts. Sorry about that. Yeah, don't lose track of your numbers like I did. So 1.6 times 12 is going to be, according to my calculator, 19.2 watts. Okay. Thank you for the call out. My apologies. Yeah. So this, yeah, thank you. Yeah, gotcha. Other than that, any questions? Okay. And then I will end the recording here.